I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
Space. Time.
brain,
Life. The universe.
This week, the discovery that's making waves in the world of physics. Gravitational waves, in fact. But what are gravitational waves, and why are they set to change how we see the universe in the future?
Plus, we take a look at the week's leading science breakthroughs, including a way to see heart attacks before they happen, fighting superbugs with doorknobs, and is there such a thing as being left or right-brained? I'm Kat Arney.
And I'm Chris Smith, and we're The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
First this week, heart disease. It's the commonest cause of death in the UK, and it happens when the coronary arteries that carry blood to the heart itself become furred up. Luckily, nowadays, doctors can reopen narrowed arteries and prevent them from closing up again by inserting metal cages called stents. But knowing where to put the stent, in other words, identifying the regions of the damaged blood vessels that are at greatest risk of blocking and causing a heart attack, can be very difficult.
Now help is at hand because Ramsey Camis, who's a British Heart Foundation cardiologist at Imperial College, has found a way to make these danger zones light up so doctors can actually see them using an antibody that glows.
Some of these narrowings, which are called plaques, can rupture. And when these plaques rupture, they cause a blood clot to form, and then the blood clot causes obstruction in the artery, which then stops the heart muscle from getting enough blood and therefore enough oxygen, and you end up having a heart attack. So the challenge is to identify which of these plaques are going to rupture and cause a heart attack. And up till now, this has been a very challenging field.
And of course, the reason for being interested in identifying which of these plaques might need intervention is that we now do have ways of going in and doing things to the insides of arteries to unclog them, open them up and stabilise them, which we didn't before. But if we don't know where to do that, we can't really solve the problem.
That's absolutely right, Chris. With the current technology that just looks at what the artery looks like, this is still not good enough. And therefore, developing a way of identifying these hot areas is really, really important.
But these lesions are inside the blood vessel, inside the person. So how can you see what's going on in the wall of a blood vessel inside a person?
This is the great advantage of using what we call molecular imaging. So we've developed an antibody against this heavily oxidized LDL, and we've attached a fluorescent marker to that. And then we injected that into animals that mimic the disease that humans have, which is hardening of the arteries, atherosclerosis. These antibodies home into where there are high levels of these oxidized LDL molecules. And then you can visualize that using a special camera. And you can do that either in the whole body of the animal, or you can do it also by using a catheter that you can thread through inside the artery, and you can look at these deposits from inside the artery, which would be hopefully the technique that we'll be using when we take this work further into humans.
And when you do this, do you actually find it flagging up areas of the walls of arteries, which when you look later using other techniques like looking down the microscope, do seem to have areas that look prone to rupturing?
Yes, absolutely. So when we look more closely at those areas that light up with our technique, you can see these areas have heavy load of white blood cells, which are called macrophages, that congregate in areas of dangerous plaque. And we've also taken this forwards, and when we stain atherosclerotic sections, which are taken from people who have had atherosclerosis or hardening of the arteries, you can see similar pattern as well.
This strongly suggests then you have got something which can home in on these hotspots. You would traditionally go in and open up the artery with a balloon and then put one of these wire cages, these stents in there to hold the artery open.
Well, yes, that would be one thing to do, but as technology moves forwards, there would be maybe other ways of treating that part of the artery without even having to put in one of these stents. One of the things we are working on is attaching therapeutic molecule to the antibody itself, so that as the antibody homes into where the dangerous area of atherosclerosis is, it will also deliver a drug to that site and in a very specific manner.
And are we far away? As in, how long have I got to survive without having an MI, a heart attack, before I can be the beneficiary of this?
Well, Chris, that all depends on how well our next bit of work goes. As you know, in science, things are unpredictable. But if you give us at least 5 years, hopefully we'll be at a stage where we can try and recruit you as our first in-man patient if you are interested. And
I prefer to be the second, actually. It's always good to be the second, isn't it? Because then the first poor guy finds out what the pitfalls are.
Well, yes, absolutely. I very much would encourage you to keep talking to us, and we will keep updating you with our progress on how we're getting on with getting this into humans.
Something to look forward to. That's Ramsey Camis on the study he's just published in Nature Scientific Reports.
Florence Nightingale's design for hospital wards is largely out of favour these days, but the interior decor of a century ago, including brass door handles, might be about to make a comeback. Now, that's not so much on aesthetic grounds, but because, as Southampton scientist Bill Keevil has discovered, copper-rich alloys have a very powerful antimicrobial effect capable of blitzing both bacterial superbugs, like MRSA, and also viruses, like the flu.
Humans are very tactile people, and we don't wash our hands very often. So what that means is we might go to the toilet, and particularly men do not wash their hands, and then they walk around touching contact surfaces such as door handles, push plates, stair rails, things like that. And then if someone else comes and touches that surface, they can pick up the bugs.
And how long will MRSA remain on some of these surfaces? You've talked about push plates on doors, door handles. How long will it stay there in a viable state so a person coming along could pick it up?
Oh, we're talking of very tough bugs here. They will survive weeks on a dry surface. And the problem is, of course, how often do we clean any surfaces, even in hospitals? We don't have 24/7 protection just from standard cleaning practices. So that's why we're interested in antimicrobial metals such as copper.
And how do they work? What have you found?
Copper's a very interesting metal. It's actually quite reactive, and we found that with bacteria, it stops the bacteria respiring, so they stop breathing. It can punch holes in their cell membranes so that their constituents leak out, and it can destroy their DNA.
How did you actually find this? What were the experiments you were doing to show that this is the case?
Well, because we're interested in touch surfaces, we developed a model system where we simulated a hand touch onto a surface and put in several million MRSA onto those surfaces. They started to die literally as soon as they touched the surface.
How do you think the copper is doing this? Do you know?
Yeah, copper is a very reactive metal. It takes part in oxidation reduction reactions. So, for example, when it punches holes in bacterial cell membranes, they're made of lipid, a kind of fat. And the copper oxidizes that lipid, and that effectively punches holes into the lipid membrane. The copper also forms reactive oxygen species, and these species, molecules such as peroxide, superoxide, hydroxyl radical, attack and destroy proteins, attack and destroy fats, lipids, and they attack and destroy DNA.
Your hypothesis then is that when the bugs are on that surface, the copper is producing all of these chemicals. The bugs find themselves in a really hostile environment and it just destroys them.
Absolutely correct. And in fact, we have microscopy procedures where we can use special fluorescent stains, and you can actually see the production of these reactive oxygen species in real time as the bacteria touch down on the copper surface.
Has anyone tried doing the experiment for real putting these sorts of treated surfaces into a hospital environment and seeing if it does cut down infection rates?
Well, yes, it's been very exciting that partly out of the lab work we started, people have been putting different copper alloys in hospitals all over the world. And in every case, they're reporting something like a 90% reduction in the number of bugs you can actually detect on the copper surfaces. And what's really exciting, a study was undertaken, 2 hospitals in New York, 1 in Charleston, and there, looking at all the data, they're reporting a 58% reduction in infection rates. So I think that's a classic example of translation from the laboratory into the real world setting.
Are researchers and technologists not already using silver in the same sort of way?
Well, that's an interesting one, because if you ask people, particularly in the clinical field, name an antimicrobial metal, they might suggest silver. But in fact, we've done comparable experiments comparing it with copper. You can put MRSA onto a dry silver surface, and the MRSA survives quite nicely for 24 hours.
So what are you advocating then? We go back to the good old Victorian days of copper and brass doorknobs on every door, and this should solve the problem.
Well, the Victorians were not completely stupid. And it's certainly interesting that there was an American physician, Phyllis Kuhn, about 25 years ago. She noticed that when they started to take the brass door handles and push plates out of her hospital, the infection rate started to go up. And she actually warned people back then, that this might be a problem. So we're not saying go back to brass. I think you go back to one of these modern alloys. And of course, the architects love this now because the alloys have got a whole range of different colours and textures. So they're really starting to switch on to this as well.
Bill Keevil, and he published that work this week in the journal Applied and Environmental Microbiology.
What you end up with is, in effect, this sequence that you've added, precisely inserted in the targeted position in the genome.
In this month's Naked Genetics podcast, we look at the hottest new biotechnology technique to hit the headlines since forever. CRISPR has big implications for health, plus linking genetics to lifestyle, and our gene of the month is black and white and very cute. Listen and download now at nakedscientist.com/genetics. You're listening to The Naked Scientist with me, Kat Arney, and with Chris Smith. Still to come, why scaring animals could be good for the environment, and we'll be joined by Astronomer Royal Martin Rees and UCL's Andrew Pontzen to talk about the latest gravitational waves discovery.
First, though, it's time for this week's myth conception. So, Kat, what bit of bad science have you been wrapping your head around this week?
Well, this has been suggested to us by Simon Strick to look into. Now, if you've been killing time on social media sites such as Facebook, you've probably had a go at some of the tests and quizzes that pop up from time to time, such as what country describes your personality, or what shaped pasta would you be? One that's recently been doing the rounds claims to be able to tell whether someone is more right-brained or left-brained, and in turn how this affects their personality and character, how you go through life and the decisions you make. According to the typical blurb, left-brained people are more organised and systematic, while right-brained people are more creative and intuitive. Known as hemicity, according to some psychology researchers, it's an attractive idea, especially if you want to blame your lack of bright ideas or organisational skills on the sidedness of your brain. But is there any scientific truth to these tests and what they claim to be able to tell us about ourselves? Well, it's obvious from looking at the anatomy of our grey matter that the brain is divided into 2 halves, or hemispheres. And neuroscientific studies have shown that specific cognitive abilities, that's things like vision, movement, language and much more, can be found in 3 different types of patterns in the brain. Some tasks, such as general attention, are done equally in both halves of the brain, as is the wonderfully named executive function. That's the ability to plan and control the things you do. Other abilities, such as vision, are found in both halves of the brain, but specific to the opposite side of the body. For example, the motor cortex in the left side of your brain controls the movement of the right side of your body. And then there are some tasks that are specific to one hemisphere. For example, language and mathematical skills seem to be localised to the left side of the brain for people who are right-handed, meaning their left hemisphere is dominant. But music and spatial processing, being able to figure out shapes and spaces, is usually found in the right side of the brain. Now, it's this discovery that seems to have led to the idea that left-brained people are good at maths and analytical stuff, while right-brained people are better at all that creative gubbins. But in fact, this is a vast oversimplification of the way that both sides of the brain work together. And it's certainly not true that someone's general personality is located in one half of their brain rather than the other. For a start, there's a huge amount of interconnectedness between the two halves of the brain, and information flows seamlessly between them through a thick cable of nerves known as the corpus callosum. A 2013 study using fMRI brain scanning showed that there doesn't seem to be a neuroscientific basis for the idea that people are predominantly left or right-brained based on brain scans from more than 1,000 people aged from 7 to 29. While there were local examples of certain different tasks tending to be done by the left or right brain, there was no overall bias to either side. So, does it really matter? Surely social media quizzes are just a bit of fun to pass the time during your lunch break, and no one takes it seriously, do they? But I think it does matter. We like to put people into boxes, and giving someone a simple label like left or right-brained doesn't really reflect the underlying plasticity that we all have to tackle life in a range of ways. Telling someone they're right-brained so they're going to be no good at maths, or left-brained so they'll never be creative, is limiting, and it's not based on sound science. So let's stop trying to label our brains, and let's label this particular idea as a myth.
Now, thank you very much, Kat. We'll have another myth conception for you next week. In the meantime, if you've heard of a potential myth that you'd like Kat to delve into, then you can email chris@thenakedscientist.com or tweet it to @nakedscientists, and we'll take a look.
New research published in the journal Nature Communications suggests that when it comes to controlling populations of wild animals, we've, at least in part, got it wrong. Normally, we cull deer or elk because their large numbers have significant impacts on the environment. But it turns out that simply fearing predators may be as effective as predation itself at keeping species numbers in check. From the Naked Scientist team, Greer Jackson.
This is the sound of a raccoon having a very happy time foraging on a beach in Canada. They're so cute and cuddly with those stripy tails and bandit masks, but actually, they're a bit of a nuisance to those who have to live side by side with them, as my Auntie Elaine found out when she moved across the pond.
We decided to landscape the back garden, so we had all this fresh sod delivered and laid. It looked lovely. Anyway, we left our garden that night, only to come down in the morning to find all the turf had literally been rolled back like a carpet. Beautifully done, complete straight lines, no damage to any of the grass. We'd no idea who or what could have done it. We never suspected the raccoons, so we rolled it all back into place and stamped it down. And the next morning we woke to the same scene. And so began the battle. It actually went on for weeks. It turns out they can roll the lawn up indefinitely, looking for fresh grubs and worms. We finally won with a mixture of cayenne pepper and water sprayed on the grass, and apparently raccoons hate it. Actually, it took a lot of diligence on our part, but gradually they stopped. Or maybe they actually just found a fresh garden to terrorise. Who knows?
Garden wrecking aside, these raccoons have succeeded in being such a nuisance, in part because of us humans.
So my name is Justin Sarasi, and I am a PhD student at the University of Victoria. Humans have succeeded in wiping out large carnivores and habitats across the globe. And one of the major consequences is outbreaks of the things that these large carnivores eat. So things like deer and elk, or smaller predators like coyotes and raccoons. And so these species can devastate the plants and animals that they consume when the large carnivores are no longer around to keep them in check.
And so normally people's solution to this is just to trap and hunt them. But your research is showing that that isn't enough.
Yeah, exactly. So we've attempted to control these outbreaks through hunting and trapping programs. But what we're doing there is we're killing some of their prey. But what we can't replicate is this fear that a large carnivore would instill in all of its prey essentially all the time, which can lead to reductions in prey foraging behavior and essentially play a major role in keeping the populations in check.
How did you find out or come to the conclusion that fear is really important here?
So we came to that conclusion through an experiment that we did in the Gulf Islands of British Columbia in Canada. So this is a coastal archipelago in which all of the native large carnivores have all been killed off. It's essentially raccoon paradise. So there's nothing to keep these smaller raccoon predators in check. They're essentially devastating the small songbirds and the intertidal crabs and fish. And we had the hunch that this had something to do with the fact that they no longer had anything to fear.
So you had the hunch. How did you test it?
We effectively reintroduced just the fear of large carnivores. So on multiple islands across multiple years, we would choose shoreline sites, and we would play either the sounds of large carnivores, so in this case, barking dogs, or non-scary control sounds. And the way we would do this is we would hang speakers from a tree, and we monitored the behavior of the raccoons and the abundance of their marine prey. And we found that when we reintroduced just the fear of large carnivores, this has such a strong effect on raccoon behavior that you actually see an increase in the abundance of the crabs and the fish that raccoons eat.
How much of a difference, though, are we talking about here?
This 66% drop in raccoon foraging led to pretty substantial increases in the abundance of their prey. Some of their major prey types are small intertidal fish, which we saw an 81% increase in the abundance of these fish. And also large intertidal crabs, species called the red rock crab. We saw a 61% increase.
It's interesting to hear that fear alone had such a big impact. Are you then advocating that we should be installing, barking trees all over the world over? Is there evidence to suggest that this would work in other species besides raccoons?
Yeah, there is evidence to suggest that other species would be similarly sensitive to just the sounds of their predators. However, it's unlikely to be an effective long-term solution. So, like you said, if you've got a tree that's been barking at you for 3 months, you're going to eventually learn that that tree's not actually a threat. So what we would suggest this study really shows, the main conservation implication is that we actually need to promote the conservation and potentially the reintroduction of large carnivores, or even allowing large carnivores to naturally recolonize.
That's Justin Sarasi from the University of Victoria in Canada. Now, this week, news broke that the Great Barrier Reef is in worse shape than previously thought due to ocean acidification. The Great Barrier Reef is one of many populations of corals worldwide. And corals, although they look like plants, are actually colonies of animals. Tiny polyps, in fact, which are almost like minuscule jellyfish. They cluster together and they gradually build up a calcium carbonate exoskeleton. Living alongside them are algae, which provide much of their energy. Georgia Mills went to find out a bit more about these unusual animals and the problems that they're facing.
The Great Barrier Reef may be world famous for its coral, but it's a little bit out of the way, so I journeyed to Sea Life London Aquarium to have a look at some for myself. I was taken through the blue fish-filled corridors, past the sharks, onto the behind-the-scenes tour. And in a room full of very loud water pumping systems amongst the jellyfish and the rays, I found a tank of corals and, conveniently, someone who could tell me about them.
Hiya, my name's Kat Dixon. I'm a senior aquarist at Sea Life London Aquarium. Coral reefs are very, very important. They are home to about 25% of all marine life, providing shelter, feeding grounds and nurseries for a wide range of marine organisms. And the biodiversity of coral reefs is actually believed to be one of the highest on the planet, more than even rainforests.
We're currently standing in front of a big green tank with several samples of coral in it. So what am I looking at here?
This is where we frag and grow our corals. So we take a large piece of coral, break a little bit off, and then grow it up here. Some of them we actually get from Heathrow Customs that have been confiscated at the airport, and others we get from other sites.
When I think of corals, I tend to think of quite brightly coloured things. These in here, they all look a bit brown. Why are these not brightly coloured?
At the moment, because it's early in the morning, the lights aren't on yet. So when the lights come on, all the algae will come out and they'll be a lot brighter.
Well, as much as I like it in this room, there's loads of jellyfish over there, there's corals, there's loads of sea plants. Shall we go somewhere a bit quieter?
Yes, let's do that. So yeah, there are many threats facing coral reefs at the moment. Some of these include destructive fishing practices, like bottom trawling can dredge up the bottom of the sea and damage the corals. Pollution, farm runoff can be toxic to corals and also smother them with algal blooms, and then they can't have access to sunlight. And also climate change is quite a big threat that corals are facing at the moment.
And the reason why climate change is such a big worry is because it attacks the coral in multiple ways. Firstly, there's the coral bleaching, which is where increased temperatures are causing coral to actually expel the algae that provides them with their colour and their energy. This leaves them unable to grow properly. Secondly, there's a bigger risk of catastrophic weather events physically damaging the reefs. And thirdly, there's something called ocean acidification.
Ocean acidification is where the excess carbon dioxide in the atmosphere is actually being absorbed into the oceans, and this is forming with the seawater a carbonic acid, which is reducing the pH of the ocean. This in turn is forming with carbonate ions that the corals would usually bond with to create their calcium skeletons, and therefore they are not able to grow and build their skeletons as they should be.
Scientists know from lab experiments that higher acidity harms coral growth. But is the small pH change in the ocean actually causing any problems for the corals? Or could it be one of the many other human impacts that's stunting their growth? A study just out in the journal Nature has taken the science outside of the lab and into the ocean and has finally revealed the answer. I called up the lead author, Dr. Rebecca Albright, while she was at the AGU Ocean Science meeting.
We wanted to effectively restore the chemistry of seawater that was flowing over a coral reef community in the natural environment to conditions that would have been expected under pre-industrial scenarios, and then monitor how the reef responded. We did this by adding sodium hydroxide, which is a base or effectively an antacid, to the seawater in order to increase the alkalinity of that seawater that was flowing over the coral reef community. And this temporarily kind of reversed ocean acidification. And then we monitored the calcification response. And what we found was that when seawater chemistry was restored closer to pre-industrial conditions, coral reef calcification was enhanced. So these results really represent the first piece of strong evidence that ocean acidification is already impairing coral reef growth.
As well as this evidence, this study also shows that if you restore acidity back to normal, the corals can grow again. So could this be the answer to our problems? Could we use Rebecca's technique to engineer the oceans to be like they once were?
Alkalinization of the oceans has been suggested as a geoengineering technique to mitigate ocean acidification impacts. However, we are very much of the opinion that this is not a scalable solution to mitigating ocean acidification impacts for global marine ecosystems over the long term. The Great Barrier Reef itself is over 2,000 kilometers long, and ocean acidification is a chronic problem that continues to worsen as the oceans continue to absorb carbon dioxide from the atmosphere. So it's really important to realize that the only solution for mitigating ocean acidification impacts and preserving coral reef ecosystems into the future is to drastically cut carbon dioxide emissions.
This was a sentiment Kat back at Sea Life agreed with, as corals are clearly worth keeping, whether they're in the Great Barrier Reef or on the shores of the UK.
There's some in Scotland and Ireland.
Oh, that's too far away. I was hoping you were going to say the Thames.
Well, yeah, no, afraid not.
Kat Dixon at the Sea Life London Aquarium, and before her Rebecca Albright from Stanford University. They were speaking with naked scientist Georgia Mills.
Now it's time to move on to the main section of our show. Wrap your ears around this. Did you hear it? That sound signifies a passing gravitational wave, and it's something that Einstein predicted 100 years ago with his theory of general relativity. Scientists have been scouring the universe for gravitational waves ever since, and this month the team at the Laser Interferometry Gravitational Observatory, or LIGO for short, announced they'd finally found one.
Ladies and gentlemen, we have detected gravitational waves. We did it.
We did a lot of running from office to office, telling our colleagues, have you seen this? You know, it's amazing. So it was pretty fantastic.
We'll have a whole new way to look at our universe, which is pretty exciting.
It's as if we are now listening to the sky as well as seeing it So it's going to see objects that are different, that can't be seen in any other way.
And we can see so cool things, like black holes colliding. It's really opening up of a new era.
Sheila Rowan, John Kaufman, Norna Robertson and David Marsh there. We'll be hearing from them all later in the programme. But what are these gravitational waves? How were they found? And why does the discovery matter? To explain, first we need to go back several hundred years to the birth of the concept of gravity itself and the Cambridge scientist Isaac Newton. He was at Trinity College and, appropriately enough, so is the Astronomer Royal, Martin Rees, who's with us today. First of all, Martin, what was Newton's intellectual leap in understanding gravity?
It was first great unification. He realised that the force that holds us to the ground and makes the apple fall is the same force that holds the moon in its orbit around the Earth and holds the planets in their orbits around the sun. He learned that this force affects all substances equally and that it obeys a so-called inverse square law, which means that if two objects get twice as far away from each other, the force gets 4 times weaker. And this law explained very well all that was known at that time about the orbits of the planets. But it breaks down in 2 ways. One way is if things go at nearly the speed of light, and the other way is if gravity was very strong. Gravity in the Earth and in the Sun is not that strong, but we imagine that there are objects in the universe where gravity is much stronger. And
black
for
holes,
those,
for example?
And the extreme phenomenon is a black hole, which was one of the great consequences of Einstein's theory, and Newton's theory breaks down under those extreme conditions.
Along comes Einstein quite a bit later, but how did Einstein change that?
Well, Einstein didn't really overthrow Newton. He extended and transcended Newton, and his theory allows us to correctly describe what happens under extremes of strong gravity and high speed, but also it gave us a deeper understanding into what gravity was. It wasn't really clear to Newton why it should be an inverse square law, why all objects should fall at the same speed, whatever they were made of, but that became natural when Einstein saw that this was really a consequence of space itself. Space interacts with mass, and the mantra is matter tells space how to curve, space tells matter how to move. And there's an interaction between the behaviour of space and the matter in it.
Einstein puts forward the idea of this concept of space-time, where the fabric of the universe is this notional entity space-time, and big things that are very gravitationally active will exert an effect or an influence on that space-time.
Yes, space itself becomes a sort of active arena where things happen, and the strongest gravity is around black holes. And if gravity changes, if for instance 2 black holes fall together, then there was an issue in that we thought that nothing could travel faster than light. So if 2 black holes crash together, for instance, something must go at the speed of light in order to cause a change in the gravitational pull felt by distant objects. And so there must be some sort of wave that transmits information. And so Einstein generally predicted that if things change, then they must emit gravitational waves. And the trouble is that these waves are extremely weak, and they're only emitted by very violent events indeed. That's why they've been so hard to find.
And how do we know that Einstein got it right?
Well, there have been lots of tests of Einstein's theory. Classically, soon after he proposed the theory, there were tests of how light was bent when it passed close to the sun during an eclipse, and astronomers have found evidence for black holes. But we'd really like to have detailed models for what black holes are like. Theorists can calculate what a black hole ought to be like, what shape it would be, but it's been this discovery of gravitational waves which has really helped to clinch that, because what's been discovered is that we get this chirp of gravitational radiation that we just heard earlier on, and that's thought to be due to 2 black holes spiralling together. They're in orbit around each other, they emit gravitational waves, that takes away energy, and eventually they coalesce and merge and then form a single black hole. And this effect is predicted by Einstein's theory. We can calculate what ought to happen, and what's marvellous is that what's been observed to happen is exactly what you would expect.
Martin, thank you very much. That's the Astronomer Royal, Lord Martin Rees from the University of Cambridge. Martin will be back on the programme a bit later on when we'll actually be looking a bit more into what these gravity waves are going to tell us, not so much about the past, but the future ways in which we're going to investigate the universe. Kat.
Now, as Martin Rees has just pointed out, one of the predictions Einstein made that hadn't yet been observed were the gravitational waves. And this is what the LIGO team found this month. Greer Jackson was there for the announcement.
Ladies and gentlemen, we have detected gravitational waves. We did it.
But how did they do it? They announced the results from the States, but there was a special meeting for us Brits in London, and this is where I met Norna Robertson, who's helped detect these elusive things.
The event that we saw was two black holes which were orbiting each other, and they're also moving towards each other because they're losing energy as they orbit each other, and so they speed up and go round and round faster and faster until they finally merge. And it's that final in-spiral and merger, which happens in a fraction of a second, that produce a big burst of gravitational waves.
And that's rippled across the universe to us. How long did it take to reach us, though?
The event happened something like 1 billion years ago, 1 billion light years away, and it's taken all that time to ripple across space towards us and pass through the Earth on September the 14th, 2015.
It's quite remarkable, really, isn't it?
It is remarkable. It's wonderful. There have been many, many people involved in developing detectors and developing all the analysis techniques. And for all of us, this is really a momentous occasion.
Alongside Norna, something like 1,000 scientists across 16 countries have been working together for 25 years. And like Norna, Sheila Rowan from Glasgow University has spent her whole career searching for them.
I wanted to be a scientist and wanted to be a physicist, I think, since I was about 9 years old. When I was young, I couldn't think of anything more exciting to do in life than spend it studying these big questions in the universe. When you go out and you look up, where did it all come from? What's out there? How far does it go? And I've been lucky enough that I've been able to spend my life working in this area and doing that.
Lucky enough to also see all her hard work come into fruition. But how did LIGO detect them?
When they're produced, of course, there's a huge amount of energy as two black holes collide, but then that's got to spread out and travel across the universe. So by the time it gets to us here on Earth, it's a tiny signal. And that means it's hard for us to build instruments that are sensitive enough to do that. And the way we do it is we take light from a laser, we split that laser light into two, and we send it out along 2 4-kilometre long paths. It hits mirrors at the ends of those paths. Those mirrors send the laser light back. The light then adds up again there. And whether it adds up so that you get a bright spot or whether it cancels itself out and you get a dark spot depends on how far the light has travelled on that 4-kilometre path. Now, what a gravitational wave does is it changes the lengths of the arms, the paths that the light has travelled. And fundamentally, it does that by shaking the mirrors that we've put down. The trouble is it doesn't really shake them very much. It shakes those mirrors by about 1/10,000th of the size of a proton inside an atom.
So how would you ever measure that?
It's a big challenge, and that's one of the reasons it's taken decades of work to do this. And there are various things that are key. One incredibly important thing, of course, is to take those mirrors that the gravitational wave's going to shake and make sure that nothing else shakes them. So we couldn't just sit them on the ground because the ground moves all the time. It shakes due to faraway earthquakes. It shakes just due to people driving cars past. So we can't do that. Instead, what we do is we take the mirrors and we actually hang them.
Now, this isn't like how you'd hang a mirror on the wall, no siree, because a gravitational wave passing through would move a mirror by less than the width of a proton. And all this other stuff that Sheila mentioned, seismic activity, cars even, would move the mirrors and could give us a false positive. So how do you make a motionless mirror, I hear you ask? One of the key things is what you hang the mirror with. LIGO have used ultra high-tech glass or silica to hang it because silica molecules don't wobble around too much. You can think of this as kind of like the fanciest shock absorbers around. This makes the mirror almost motionless. The final key component is the fact that there are multiple devices that record the movement of the hundreds of components that all connect to the mirror. Knowing how much these various bits of machinery move, it means that with great precision, they can account for these tiny movements. Now that they've made these motionless mirrors and even detect one gravitational wave, when will they detect the next one?
We don't know the answer to that yet. We do have more data. We just haven't had time to look in there yet and see what's in there. So we don't know. You'll have to wait to hear back from us, but we promise we're looking hard.
Watch this space then.
Or as my colleague in Glasgow often says, watch this space time.
It's going to become my new catchphrase. Sheila Rowan from Glasgow University, and before her from Caltech and the University of Glasgow, Norna Robertson.
You're listening to The Naked Scientists with me, Kat Arney, and Chris Smith. This week, we're discussing the recent discovery of gravitational waves. We've had a lot of questions come into our web forum and by email, so we thought we'd put them to UCL cosmologist Andrew Ponson, who's a regular here on the show. Hi, Andrew.
Hello.
Now, we've had a tweet in from Ed Wilson, and he's linked us to some research from Harvard saying these gravitational waves are coming from a single star, not two black holes. So how do we know this gravitational wave came from two black holes colliding, and how do we know where they are?
Oh, gosh. Well, welcome to the world of theoretical physics where, any new piece of data gets people tremendously excited and people start poring over it in a lot of detail. One of the most striking things about the wave that was detected is just how closely it matches what people expected to see if two black holes merge. So it would be very challenging to think it's something substantially different.
And do we know exactly which black holes they were and where they were in space?
Not exactly, no. I mean, certainly we don't have any sense of, we've seen these black holes before and now we know they're merging. This is a totally unknown object until the moment at which its gravitational wave arrived. Now, the plan is in the long term to be able to accurately work out exactly what direction did a gravitational wave come from. But the trouble is, at the moment, we're not quite able to do that. And the reason is that at the moment there are two detectors running. And the whole idea of being able to pinpoint it on the sky requires a kind of triangulation.
So you need another one, basically.
You need another one.
At least another one.
You need at least three if you want to be able to find a pinpoint location on the sky to point a telescope and say, yes, it came from that direction.
Do we know anything more from these results about what gravitational waves are actually made of? Because we know for light beams that they're made of photons, and sometimes people might have heard this word gravitons, the idea that gravitational waves might be made of particles as well. I mean, does this move us any more forward with this kind of idea?
Oh, well, unfortunately, this doesn't really help us with that particular puzzle. I mean, in the same way that experiments were done on light long before it was realised that actually you could imagine making light dimmer and dimmer and dimmer until eventually, rather than it behaving like a wave, you're just left with single particles coming out of your light bulb, which is what we mean when we say a photon. You could imagine that a similar process might be possible with gravitational waves, and somehow you make their intensity smaller and smaller and smaller until you're left with a single graviton. But the intensity of these waves is far too high for us to be able to say anything about that at all. So at the moment, this discovery really doesn't shed any light on that particular direction.
There's been so much talk over the past couple of weeks about this discovery. It really has been incredibly exciting, certainly on social media and the national media, the global media. Do we actually believe it? Do you reckon it really, really is real this time? Because there's been false alarms in the past. We're going to hear about one of those later. But is this the real deal? What do you reckon?
Well, I mean, as a scientist, you always have to have a little tiny bit of doubt left. However, for what it's worth, I, and more importantly, an awful lot of the world's experts on gravitational waves are extremely convinced by this particular detection. And the reason is twofold. First of all, you can simply go and look at the data and compare it to the theoretical predictions for what those waves should look like. And you can see what an exquisite fit the data produces. But on top of that, if you look in that paper, you'll also find a lengthy discussion of what are the statistical chances you could be fooled, that something could turn up in your detector that looks very much like this but actually isn't. And they put the chances extremely low. And so my money's on this being absolutely real.
Brilliant. Thank you very much. That's Dr. Andrew Ponson from UCL. And if you want to find the paper, they'll be up on our website. That's nakedscientist.com.
Now, if you cast your mind back to early 2014, you might recall news that a group of American astronomers were working with a telescope called BICEP to study the sky, and they were claiming they were finding remnants of gravitational waves from the Big Bang. And to much fanfare, they published their findings, reporting the discovery of these ripples. Unfortunately, subsequent tests showed that what they were actually seeing was down to space dust. But their search continues, though, because they're trying to find and use these waves to probe what happened during the earliest moments in the history of the universe following the Big Bang. This is a period that's called inflation, but it's further back in time than traditional telescopes can see, which is why we need gravity waves to probe in there. Greg Jackson.
If you're anything like me and love a bit of boogieing, you might be dancing around or jiggling around in your seat. And you know what? If you are, you're making gravitational waves. Pretty cool, huh?
Yeah, it is pretty cool. Undetectably small, but nevertheless, you're creating gravitational waves in it.
Yeah, David Marsh is right there. They're so small we can't even detect them. It's only the ripples from massive events that we can pick up on, like two black holes colliding. But what about the biggest event in the history of the universe? The Big Bang.
Oh, yeah, absolutely. So the inflation theory, the sort of bang behind the Big Bang, this would send gravitational waves rippling throughout the universe.
But how would John Kaufman look 13.8 billion years ago into the past? Well, with something called the CMB, the Cosmic Microwave Background. This is a faint glow of light that fills the universe with nearly uniform intensity. It's the residual heat of creation, the afterglow of the Big Bang, streaming through space these last 13.8 billion years, much like the heat from a sun-warmed rock, re-radiating that heat at night. Notice, though, how I say nearly uniform intensity. David Marsh again.
When we look at the sky at microwave wavelengths, we would see the cosmic microwave background, and it would seem almost having the same temperature everywhere. So we can compute the temperature is 2.7 Kelvin. What is it, minus 271 degrees?
Pretty cold then.
Cold, yeah. And then you can compute it. You can first, second, third, fourth. And then at the fifth digit, you see that it starts to vary. So at that level of temperature, it starts to fluctuate.
Temperature fluctuations only after the fifth decimal place. That's absolutely bonkers. But these tiny changes in residual heat are critical to the study of the universe because it's the fossil imprint of those Big Bang light particles tell us about another fluctuation, the ripples that gravitational waves made in the fabric of space-time. But members of the BICEP team, like John Kaufman, have to go to great lengths to detect them, like the South Pole. What you can hear is a video of John and colleagues heading out on a skidoo to the telescope. They're wearing so much clothing that not a bit of flesh is visible, despite it being a beautiful blue-skied and sunny day.
It can be grueling, but what our telescope does is we look for the temperature of the cosmic microwave background, the E-mode polarization, and the B-mode polarization.
And so this polarization you're looking for, what's that?
How light is an electromagnetic radiation, it means that there's an oscillating electromagnetic field, and if it has a preferred direction that it likes to oscillate, if you imagine you hold a string and you whip your hand up and down, you're creating a wave on this string that's polarized in one direction, the up and down direction. If you whip your hand left and right, you'll create a polarized wave left and right. It just means that there is a preferential axis to the wave that you've generated.
And that's what you detected.
Right. Only gravitational waves can create B-mode polarization at this cosmic microwave background time. And it became clear that we were seeing something. And none of us believed it. We all expected it was some sort of systematic contamination. And so we set about for a long time to just try to convince ourselves that what we were seeing wasn't real. All sorts of crazy ideas of what this could be, including one of my favorites, which is the communication satellite might have been interfering with our telescope. So we ruled that out. Finally, everything was ruled out. It looked like this must be on the sky. And then, of course, we published, and articles started popping up, New York Times, then, NPR, then, everything, all sorts of news sources. And then things got very interesting.
And you know why it got interesting? Because of something seemingly very uninteresting. Dust. Yep, you heard me right. Dust. Things like comets and supernovae all leave dust in their wake, and this dust can imitate the light polarization sign that John is looking for. But when another satellite called Planck came along, it suggested that it's not really quite that simple. John and the BICEP team continue to look for this light polarization and hints of gravitational waves down at the South Pole, but now the LIGO team have found them. Should John just give up the ghost, now that it's no longer a ghost?
So these gravitational waves, the one that experiments like BICEP are looking for, are pretty significant because they would be evidence for the theory of inflation. And the theory of inflation is one of the most important theories that I think humankind has ever developed, in the sense that it is the sort of why are we here? And inflation answers that. And so while there is a significant amount of evidence for it, the smoking gun of this has not been detected, and that is these gravitational waves.
It's big stuff, because that inflation is how the universe grew rapidly from its origin as a tiny, tiny point to a much bigger entity in just fractions of a second after the Big Bang. You heard there John Kaufman from the University of California, San Diego, and before him, David Marsh from Cambridge University.
Now, John makes a very strong case for why they need to go on searching for these Big Bang gravitational waves. But I wonder, what about LIGO's gravitational waves? Why are they so important, and why are they revolutionising physics and astronomy? Well, let's put this to our two guests who are with us this week. Martin Rees, Astronomer Royal and a member of Trinity College, Cambridge, and also Andrew Ponson, who's a cosmologist at University College London. So starting with you, Martin, why are physicists and astrophysicists so excited?
These gravitational waves are predicted by Einstein's theory, and in fact they're about the most distinctive and remarkable prediction of the theory. And what is amazing is that the observations seem to fit extremely well with the calculations. So it's a really strong vindication of Einstein's theory about 100 years after he proposed the theory.
Are there any other things that we should do in order to validate, vindicate and corroborate Einstein's predictions?
Well, we still don't know exactly what shape these black holes are and how fast they're spinning. And of course, as astrophysicists, we'd like to know how the black holes got there. What was the evolution that led to them? So there's a great deal for astrophysicists to do.
We've heard a lot of people saying these gravitational ripples arrived from 1 billion light years away. How do we know where those black holes were situated out in space?
The signal was detected in two detectors about 2,000 miles apart. And there was a slight time lag between the two detections, and that tells you something about the direction, because it tells you how much longer it took the waves to get from one to the other going at the speed of light. And if we had 3 detectors, we could do a kind of triangulation. But I think we should realize what amazing technology this is. We're detecting this event which happened millions of times further away than all the stars you see in the sky, and it's been detected by these instruments, even though it's a tiny jitter in the mirrors that we heard about. A very tiny effect. So it's amazing technology.
1/10,000th the diameter of a proton is the catchphrase they're citing.
That's
Phenomenal.
right. Another way they would present this is it's like measuring the diameter of a human hair at the distance of Alpha Centauri, the nearest star. So it's amazing precision. So it's the engineers who really deserve far more credit than the theorists.
And Andrew, is it true to say then that in the past we've had some of our efforts at astronomy frustrated by light being interrupted on its course to us by stuff like dust and other materials, but these gravitational waves should pass straight through everything, so we should in theory not get them occluded by anything in their way?
Well, that's certainly true, but I think that there's an even bigger difference when you start observing the sky using gravitational waves, which is the kind of objects that you're picking up are simply things that you would never see with a traditional telescope.
So this really is a new vista?
Oh yes, and I mean even now we're talking about two black holes about 30 times each the mass of our sun merging. I mean, if you just stop and think about what that actually means for a second, it's actually mind-blowing. And
I can tell you're excited. So on a scale of 1 to 10, where would you put this?
Well, it's sort of. It's a 10.
He's lost for words.
It's a 10 in terms of scientific significance. In terms of my career, it's just a source of regret, really, because when I started, I had an opportunity actually to work on a PhD on gravitational waves, and at the time I thought, oh come on, I mean these tiny things, they're never really going to be detected, are they? So I didn't, and I worked on something else, and now I look like a bit of a fool.
Martin?
No, I would put it 9 out of 10. In a way, the primordial gravitational waves, if we could detect them, would be even more exciting. But they're very hard to detect. So that would be 10 out of 10. I would give these 9 out of 10. But because I'm an astrophysicist, I am interested not just in them as tests of Einstein's theory, but as part of the evolutionary story of how stars form, evolve and die. This is telling us about a new way in which stars end their lives.
Martin, wonderful way to finish the programme. Thank you. That was Lord Martin Rees and Andrew Ponson. Thank you also very much to our other contributors this week.
And finally, it's time for our question of the week. Felicity Bedford has been bugged with this question, sent in by listener Bronwyn Higgs.
The Naked Scientist's Question of the Week, brought to you in association with the Houter Wisman Foundation, supporting science and education from Alpha to Omega.
Why do mosquitoes prefer some people over others?
Some people, including me, seem to act as mosquito magnets. I asked Heather Ferguson from Glasgow University whether mozzies really do target me, or if I'm just unlucky.
This is absolutely true. We have very good evidence for a number of mosquitoes in a number of different settings around the world. So if you think you're the one in the group who's getting unfairly hammered by mosquitoes when you go out, it's probably true.
Why is it that mosquitoes find some people so much juicier than others?
Well, that is an age-old question, and I think people have been thinking about this pretty much for as long as they've been getting bitten by mosquitoes. And the short answer is that we don't actually have a precise understanding of why this happens. It's likely to be due to a complex mixture of environmental and genetic factors. It's a whole range of things, including, for example, how much carbon dioxide you're emitting when you breathe. Also, it varies in response to different components of scent and odour that people will emit.
This doesn't sound like something we can do very much about. Is it just a case of putting on some insect repellent?
Certainly, repellent is really important, and we would always advise people use that if they're going to an area where they're likely to be bitten. But there's a lot of other advantages to really researching this question. I think most notably, a lot of my collaborators in East Africa and other settings around the world have been making a lot of progress in trying to identify specific smells that attract mosquitoes rather than repel them.
That doesn't sound like something I want to be doing.
Well, it can be hard work, but the payoff can be huge, because this is something, if you can find an artificial odour that really is very attractive to mosquitoes, you might be able to use it for a trap. So it is worth the effort.
What kind of smells are we talking about here?
Some work that's been done by a colleague of mine, Dr. Fredros Okumu, who's a Kenyan scientist. He spent 3 or 4 years of his PhD working really, really hard amidst the most ghastly smells you can imagine, mixing different types of compounds at different concentrations, essentially always smelling as if he'd been locked up in a tent with a big rugby team, so really, really smelly, sweat-like odours.
Oh, delightful.
But the payoff was enormous in that he's come up with a compound that in some settings can be about 4 times more attractive to a malaria mosquito than an average person. So this is then now being taken forward with large injection of funds from the Gates Foundation, with the idea being that in the future we might be able to have an odour-baited trap for malaria mosquitoes.
Thanks, Heather. Short of finding a smelly rugby team to follow me around, I guess I'll be stocking up on insect repellent for now. Next week, we'll be answering Erica's question.
How do pheromones work in humans?
What do your pheromones say about you, Chris? I think they say you need a wash. If you can help us with Erica's question, email chris@thenakedscientist.com, find us on Facebook, tweet @nakedscientists, or join the debate on our forum. That's thenakedscientist.com/forum.
Well, that's just about it for this week. Many thanks to producer Greg Jackson for putting the show together. Next week, where do new infections come from? Join us for the A to Zika of emerging disease threats. If you'd like to send in any questions in the meantime, you can address them to chris@thenakedscientist.com. The Naked Scientist comes to you from Cambridge University. It's supported by Rolls-Royce, the EPSRC and the STFC. Until next time, goodbye.